It's just crazy. Listen to this reverb. And the filter. And the crazy thing is, this does not really have to be connected to the computer. It's actually running through this little microcontroller here. And I'm not a programmer, and I managed to write this code on my own. With a little bit of help from a friend that is going to teach us today how to program something like this, or at least the foundation of how something like this is working, so you'll be able to design your own instrument. This board that you're seeing in front of me is, oh, there we go, this little thing. I don't have enough power. You see all these holes? You can actually put here lots of components, potentiometers, knobs, sockets, switches, and then connect them through here to the microcontroller here, which allows you the flexibility to design your own synthesizer, which is mind-blowing. This is designed for musicians, and this is designed for musicians. So together, this is an insane world of possibilities that I cannot wait to share with you. Today we're going to look into how to write the code for this in Arduino. Let me just take this down. We're going to look into how to write the code for this in Arduino, and we're going to meet Chris, who is an engineer and has been working for a decade as a professional engineer in hardware and software. So he's going to explain how things are done, because I'm a musician myself. I'm a designer and I teach design, product design, but I always work with engineers to help me with the technical side. So he's explaining really well how things are done. And if you're in Berlin, we're actually going to run a physical workshop in August for 3 weeks that you could actually join and get one of these beasts to design your own thing. Now, we're also going to run these workshops in other locations around the world. So if you're a teacher or a musician and you want to get a few people together, if you want to learn how to program in Arduino and build your own instrument, then these are definitely for you. Just send me an email or join us on Discord to get started with this. Now, before we continue, I just want to show you, so this is now connected to the computer because I am actually programming it, but if I disconnect it and take one of these little things, check this out. This is just a power bank, and it will work exactly the same. All right, this lesson is going to be valuable even if you're not working with a simple board. It's going to be valuable if you're interested in synthesis and building your own instrument. Nevertheless, you should join us on Discord if you want to meet more people like this and if you get stuck with technical issues. And you should check the links below because there are lots of resources that are related to this, because I'm designing this as a course. And part of the course is also some screenshots and some things that you might need to know. So if you're taking this seriously and you really want to build your own thing, this is your place to check. Without further ado, let's get started. So, we have a synthesizer. And it sounds like this. We're going to go through it, and we're going to explain how to do it together, Chris and I.
Let's do that.
All right. Okay, so first of all, what are we looking at here? What is going on at the top here?
In general, the platform that we're using is the Daisy Seed by Electrosmith. So, and they're quite helpful in getting us started very, very quickly. So that means if people are comfortable with maybe Arduino, which is like the easiest way to get started with electronics, then they provided a library for us, and that's what is here called the daisyduino.h in line 4. And that is the library that we can include. And this will provide us with all kinds of cool abstractions for like getting sound out of this thing.
Maybe
And
before you continue, when you say abstraction, what exactly does it mean? For instance, like the oscillator here is basically programmed. They basically
yeah,
programmed it. That's the abstraction you're talking about.
exactly. Yeah, it's programmed for us, and
Right.
we just need just a few instructions to make it actually, to have it make a sound, which is nice.
Cool. Then we have another section that's called the setup, and I see here a bunch of things. We
Yeah,
first of all have like the daisy setup. What is the daisy setup?
yeah. So in general, the setup function that is provided by Arduino here is the function that is called once, like when you just power your device, for example, or when you flash new code, then the setup function is called once. That means it's just it's just the instruction is basically executed at the beginning and then not anymore. So that's kind of important to know. And this is where we do all of our initializing. This is where we do all of the setup stuff that we need to do in order to get to the point where we can actually create audio.
Right. Why is it important to divide between things that are happening constantly in a loop and a setup that just happens once? Why not just put everything inside of the loop?
And because then things will happen over and over again, and that's not necessarily bad, but sometimes you just want to execute something once to really set the base for it. And if you would have it execute more and more usually setup functions take a lot of computational power. When you execute them over and over again, then you would have not enough power left for the actual sound that you want to make.
Yeah, so it's about efficiency, basically. You're trying to minimize the code that is running as a loop, so you can make the most out of the processing power.
Exactly. So this is the main reason.
Cool. Okay. So then I see that we also have an oscillator setup here.
Exactly. So in the beginning, we have to kind of agree on a sample rate. As someone who has worked with a DAW or something like that, that might be familiar, then we have to kind of agree everything has to work the same sample rate. Otherwise, it gets kind of confusing, and the timing will be off, and it will sound horrible. So we agree that we run on a sample rate of 48 kilohertz here. That's what we're doing in line 18. And then we get the sample rate out as a number again. So to have this number in so that we can do math calculations with it, or our oscillator needs this as a number, and this is what happens in line 19.
Right. Okay. And then I see
but we don't
that,
have to pay too much attention to like the sample rate things right
yeah,
now.
but yeah, the way that I understood it is basically this is sort of like a setup thing that I will need to have in any of my patches, no matter what. I just put it in, and then I start focusing on the more creative side. This is just like practicalities.
Exactly, this is practicalities, and this is just a setup function for the DAISY itself, because it doesn't only consist of a microprocessor. It consists of a lot of other components that need to communicate, and this is kind of the setup for it.
Right. Okay. So then when I look at the oscillator, this what I liked about this is that I really felt like I can read it. So if I would explain it myself, is like I am initializing the oscillator with a sample rate that I defined here, so 48K. And it's the same thing that I'm doing here also. So I'm initiating the filter with the same sample rate. With the oscillator, I'm also setting the frequency, and I'm just basically saying the oscillator is tuned to 100 before I touch anything. And then if I would change my knob, it would change it from that 100.
Yeah. That would be 100 hertz in this case.
100 hertz, yeah. Okay. And then we have the oscillator again, where we set the waveform, and the waveform is oscillator 1.wavesaw. I just realized that it's completely off. Yeah, so now you should be able to see better what I'm looking at.
Yes. It's
cool.
all good.
Great. So yeah, so we set the frequency. We also set the waveform. And And then this is pretty straightforward. Again, we just initiated the filter, but we could also maybe add here, I guess, set frequency. Set frequency, yeah. And then set frequency would be, I don't know, 200, and that would be like, just like we have here. This would work as well, yeah.
For the case of the filter, that would be the cutoff frequency.
Yeah, the cutoff frequency, yeah. And then we have the Daisy begin process audio. And what I understood is that it's actually coming from here. And this is, I think, the part where it gets a bit confusing. Maybe you can explain what is going on here. How is exactly the audio samples, or how is it processing the audio?
Yeah, maybe I will avoid getting into too much detail here, but in general, when you do digital signal processing, then you have a certain fragment of the audio that you look at. Let's say maybe 100 values. You have to imagine that the audio that you hear is in the computer is just numbers following each other in a with certain values, which means this is the amplitude of these numbers, or of these of the sound, basically. And that's pretty straightforward. But when you do this digital signal processing, then you always have a fragment of these numbers that you look at, and this is the thing that you put through your processing chain. Let's imagine you have an oscillator which creates like a bunch of numbers, and it kind of knows, I have to create a sawtooth wave now, and it will create the sawtooth wave for you, and which results just in a bunch of numbers. And these like 100 values, for example, maybe it's more, maybe it's less, is what we call like an audio buffer. And that goes then, in our case, into the filter. If we say, let's say it's 100 numbers, that would be the size that we can see in line 45 and line 46. The size value is this bunch of numbers. We don't really have to worry about it because the Daisy DSP library will figure that out for us. We just have to know that this is some size of this buffer that we fill with audio data.
It's, if I understand you correctly, it's like chunks of information that the processor is going to go through and spit out, like, okay, this is the number now, this is the number now, this is the number now. But it's doing it really, really, really fast, so it can actually draw the sine wave. But not only the sine wave, it could also draw the saw wave going into the filter, going into the reverb, and this is how that sounds. So it actually knows this is how the saw sounds, but now the saw is actually going into the filter. So this is how it sounds after the filter. And now it's also going through the reverb. So this is how it sounds after the reverb. And what do you want to hear in your audio, in your headphones? The end of the reverb? Okay, here's only the end of the reverb.
Exactly, yes.
Cool. Yeah, that's what I understood as well. And this is basically this line, right? Like we have an output that is like channel 0, which is like our channel 1, that receives the filter processing that's processing the oscillator. That's why the oscillator is basically inside, so there's like filter process of whatever is inside of it, and the filter is processing the oscillator. That is processing nothing because nothing is going into the oscillator. But if we would have, for example, another oscillator that goes like frequency modulation, would that also be inside here?
That would be something else. I don't think the process will take any value at all, but then you would call a function on the oscillator which sets the frequency.
Okay. But then if we would have a reverb, for instance, then the reverb would go like the filter process would go into the reverb.
Yeah, exactly. The reverb is a tiny bit more complicated because it's a stereo reverb, but in a sense that would look very, very similar, yes.
Yeah. Or like if you would have a distortion or like whatever,
Yeah,
then
or chorus effect or something like that, for
yeah, so we
example.
basically get the filter process inside inside of it, pretty much.
Yeah. You have to imagine that this oscillator process gives us a value exactly 48,000 times per second. And then this filter will process it at exactly the same rate, 48,000 times per second. And then this is what we will hear. In layman terms, you can think about it like this.
Yeah, this actually ties a lot of things now together because we were talking about the 48 kilohertz, and hertz is basically a speed.
Yeah.
Yeah, okay, cool.
So, and the DSP library makes sure that we will always get the 48,000, because if this would vary because of like certain as we talked about earlier, when the processor is overloaded or something like that, then it would not be 48,000 constantly, but it maybe would vary because the processor cannot catch up quick enough. So, and then we would have a problem because then the sound would get distorted.
Okay.
But it makes sure of that, and the Daisy, the platform that we're using, has enough power to do a lot of crazy things.
Yeah, I saw people putting like 100 oscillators on it and it didn't blink. So
Yeah, it doesn't care.
no, no. Okay, that's pretty awesome. Okay, so we have now here another section. We have a loop. So at the beginning we had the libraries, then we have setup and we set things up, and then we had the audio processing, and then right under this we have a loop. What is this section for?
Yeah, so we have to also say the audio processing is also something that is called over and over again.
So it's also a loop.
It's also a loop, which is called 48,000 times divided by size. Doesn't really matter, but this is kind of the amount where this is called. Um, and then we have another loop which comes from Arduino, which is just the default loop. It means it just run. If you think about a processor, it always runs in loops. It always runs instructions after another, and then something tells it start at the beginning and do everything again. And this is what this loop is. It's basically just executing instructions as fast as it possibly can.
Yeah, and then what I see here is just one line, filter set frequency, which is similar to what we had here also with the oscillator. But here here I had just a concrete number, 100, and here I actually have analog read A0.
Exactly. So the microprocessor that we're using, or the Daisy platform, has a way to actually detect the voltage that is on one of the pins that allow for that. And that can actually give us a number between 0 and 1023. That means if you have a potentiometer connected to one of these pins, then it can detect the value of this potentiometer very, very easily and very quickly. That means you can actually read the value, and it's going to be, if it's like all the way to the left, it's going to be 0, and if it's all the way to the right, it's going to be 1023. And this value we can detect, and we can just include in our program. And this is the way how we would interface, how we would actually add an interface, or like a real interface, to our program.
Right. When you're saying interface, like a physical interface.
A physical interface, exactly, yes.
Yeah, yeah. Okay, so let's maybe try to have a look at a new sketch. What are the things that I would basically just need to copy that are not really changing at all? I'm assuming first of all I'll need this whole section.
If you want an oscillator and a filter, then that's probably what we need to copy.
Okay, so I'm gonna take this and put it here at the top. And then in the setup, I have this thing that's also in the setup.
Yeah, we always need the daisy.init. That's the...
Yeah. And now we can start No, and we also need this guy. So
yeah, the process audio, and then the what was it called? Daisy begin, I think, function.
yeah,
Or Daisy process. I'm not sure what it's called.
yeah, Daisy begin.
Daisy begin, yeah.
This is
That goes into the setup.
that goes into the setup. So right before the setup ends. So
Yeah, as you can see, it's kind of always the same. So you don't really have to worry about a lot of technicalities. You would just copy code and then you mess with it. I think this is the way I would go about it.
Yeah, so this is basically a template file we could use to create a subtractive synth.
Yeah.
It has an oscillator, it has a filter, and the amplitude and everything is actually something that we do with just math, right? Like adding, subtracting, multiplying.
Exactly.
Yeah, cool. So this is the basics, the foundation of a subtractive synth.
Yeah, it would always look like this.
Okay, cool. Yeah, so let's start with Daisy setup. Well, not Daisy, but the oscillator setup. So what I want to do first is to add an oscillator. Maybe good to mention that is something that is important when we have an oscillator here. The oscillator is basically a name of an object, and this object we could have multiple of them. Just like I said before, like there were like people putting 100 oscillators in their Daisy patch. You could call Rowie an oscillator. So there is an oscillator by the name of Rowie, and an oscillator can do all sorts of things. If I share my screen, so this just blew my mind because yeah, so I can look at an oscillator here, and then I can see that Steven and the guys at Electrosmith, they basically wrote the code for an oscillator, and they explain here what you could actually do with it. You could define a sine wave, a triangle wave, a saw wave, a ramp, so on and so forth. And then you have also a bunch of things that you could do here. You can initialize it, which is kind of boring. Yeah, okay, I just initialize it. But then I can also change the frequency of it, and it will literally look like this. I would say oscillator 1, or like what did I have here? Rowie, for instance, dot set frequency. And then I would put here the frequency or the knob that I want to control it with, and it would just allow me the control. Same thing with the amplitude. Also, same thing with the waveform. I could change the waveform this way, and there are a bunch of other things.
You could have a knob where you go through different waveforms, which would be fun.
Yeah. So what I really liked about this is that we can actually see here a lot of words that we're very familiar with, like ADSR, for example, Ottawa, bit crush, chorus, compressor. All these delay line, all these different words that we know from music, like hi-hat, are basically programmed for us already. All we need to do is like go to a looper and see how, like what functions are already programmed for the looper. So we could say clear the loop, I guess. Trig record. So if I press a button, start recording. There are like all sorts of like functions that I could call.
Yeah, I think this is also a good time to mention that that we could potentially also have audio input in this system, like the Daisy allows for it. So you could have audio coming in from a line in or microphone or whatever. Then you can process that in the in your program as well, which is fun.
Yeah, maybe I'll bring this up because this was also quite revealing for me. When you're looking at these pins, they have color codes and they have some text on them. It's actually pretty easy to read. You can see here, this actually says audio out 1 and audio out 2. So when I'm looking at, and I hope this is recording, let's see. Yeah. So when I'm looking at the microcontroller here, all these pins, they correspond to the pins here on the screen, which means that when I need to use output 1 or output 2 or audio in, or so I could have like stereo in and stereo out. I could see that they correspond to these numbers, which are now on my board, and I can then connect a socket for them. And then we also see here the ADC, which is analog to digital conversion, which means that any of these yellow ones we could use to either use for CV in. We'll need to have like a little analog circuit for that, but basically this is where you could actually put a socket for Eurorack, for instance, for getting CV to control something, or you could have any sensor. It could be a potentiometer like this, but it could also be a light-dependent resistor or a pressure sensor or a lot of other things like a gyroscope, for instance, which allows you to really define the interaction, which I think is really the most exciting part in this. How do you actually interact with the sound that you have in your head? Yeah, so let's go back to stop sharing screen. Yeah, okay, so we have here an object from the type of oscillator, and it's called Oscillator 1. And we have also type Moog ladder that is called filter. That is the name that I gave it. And I now can write here the code to say, basically I can just copy Oscillator 1, and I need to do initiate, right?
With a uppercase I.
In it. And then I need to put here the sample rate, like this.
Yeah.
And then
maybe we can just have a patch where we have an oscillator and then it puts out a static sound for Serge to see whether everything is working, and then we can continue. And
yeah, that's probably a good idea. Okay, so oscillator 1 sample rate, and then oscillator 1 dot set frequency
with the uppercase F. Yes.
Yeah. And then I can just put 300, so that's 300 hertz. And now I have my.
So we use a sine wave. I think that would be fun.
True. I need to also do that. So
I like sine waves.
Oscillator 01 dot. I don't really remember. So what
it's set waveform.
Okay, but what I can also do is I can, let me just share my screen so I don't do it just by myself.
Oh, yeah.
But I can, if I don't know exactly how it's called, I can go and search for the object here. So oscillator, and now I can set waveform. So I can just copy.
Yeah, in the top we see all the supported waveforms as well, which is nice.
Yeah. Okay, so I can now go set waveform and then choose wave sine. Close it. And now I have initiated an oscillator with a frequency of 300 with a sine wave.
Can you check again the documentation?
Yeah.
Okay. Oh yeah, you have to. Sorry, you have to set waveform. It wants you to put in oscillator 01 dot wave sine. It's namespaced, is what we'd call it.
Oscillator 01. Like
yeah, and then dot wave sine, just like in the other patch.
Dot wave sine. Yeah. So. Yeah, I need to give it the name so it would actually know. And then we have the sine wave assigned to oscillator 1 on 300 frequency 300, and it is initiated, and it's done only once in the setup. So I know now I have an oscillator, and it is set up for sine wave with 300 frequency. Now I need to look at this line, right? Because I have now the output that is taking the filter process, but I don't really have any filter here. So I need to take out the filter. I need to put here oscillator 1 dot process like this. So my output is now getting whatever the oscillator is going to give me.
Exactly.
And I don't have anything in the loop because I'm not really... all I want to do now is just to hear if this is working.
Yeah.
I don't have any control. So I'm just going to do command U. And there's one little thing that I need to do here on the board itself. I need to press on boot and then reset. So I do this once. And that's every time that I need to change here, that I want to upload my code, I need to do boot and reset. And then I do command U, and it asks me to save. Go ahead. No, save. I'm just going to check if the camera is still recording, and it's not, of course. Okay, so now the camera is recording.
You picked the wrong board in Arduino.
Yeah. Aha. There we go. We actually have an oscillator, but we can't really control it, which is annoying. So I'm just going to reset it. Oh, I'm going to boot reset it so it doesn't... when I do boot reset, it basically deletes everything, I guess?
No, so a microprocessor has this kind of thing called bootloader, and you put it into this mode where it's able to receive a new program. It's a different mode you put it in. It's kind of a hard-coded thing on the processor, which then runs.
Okay, so now it is in this mode, so I don't really hear anything. And now I can go here and say, I guess, oscillator 1 set frequency. And instead of 300, I want to put here analog read. And I'm just going to take this large knob that is 38. So 38, I think it's A0. So A0.
An analog read will give us a number between 0 and 1023, which is very fine for a frequency.
Okay, so let's see. Ooh!
There we go.
Wow. But it's inverted.
That's a good range already.
It's a super nice range, yeah. That's a really nice sine wave.
Yeah, it is.
Ooh. That's awesome.
But like the digitally created sine waves are always better than the analog created sine waves. That's kind of the thing.
Yeah. Okay, but we're running out of time. Let's just, I just want to invert this because now it's a bit annoying. It's kind of like when I go all the way to the right, it's low.
Yeah.
And then when I go to the left, it's high. How would you invert it here?
Yeah, basically what you do, because you know the maximum value is 1023. So if you just say set frequency and then you do 1023 minus analog inside the parentheses. Yes. Like so then you know when analog read is 1023, then it's 0, and when it's 0, then it's 1023. So you kind of exactly invert it.
Got it. Okay, I need to also boot reset. And yeah.
Nice.
Awesome. Okay, let's just last thing. Let's change this to saw. To select port establish connection. That's probably because I did the reset too late. So if you get sort of errors that feel random, it's probably because you need to do the boot reset.
Yeah, it's a bit annoying that we have to do this, but it's also good because it's safer. Then you know, like I actually want to upload the code, and as opposed to accidentally uploading code.
Ooh. Well, this is awkward. We were having so much fun with that last oscillator that we forgot to record the ending for the tutorial. So thanks so much, Chris, first of all, for taking the time and explaining everything. This was super generous and really valuable. Really appreciate it. And you guys should check out Chris online. You should also join us on Discord, because if you're a musician, you're getting stuck with a bit of like programming or soldering or like analog circuits, if things do make noise or whatever, bring it to Discord and share your questions, and we'll probably find a solution. We're also running these workshops in different locations online and in physical space, so join us. And if you're into synth design, that's probably where you would want to start. Thanks so much for watching, and I'll see you in the next one.